Hello everyone, welcome back to another episode of MATLAB programming. In this episode, I'm going to work on a new feature in plotting in MATLAB. And this is one of the most important ones that we're going to use a lot. So let's get started. I would create a plot, actually a script called plot example. And in here, let me clear all and then close all and CLC. So close all would close any open window. So let me start by using figure, and all it does, if you click on it, it will create a figure, an empty figure or placeholder that we can plot our functions on it. So on the next line, let's create our x-axis, or better called time. So t equals 0, and then I'm going to create my function between 2 and 2 pi. And in between, I'm going to divide it by pi over 25. That will be the increments for this function. So then I'll create representing the timeline, and then I'll create the plot t, and let's say have sine of t, and for the markers and color, let's go with the dash R and star. R means for the red, and then a star would be the markers. And then I'm going to plot another function called t. Let's go with the cosine of t this time. And then for the markers, and we learned in the first course, Learn MATLAB Programming Under 30 Days, that how we can manipulate these plots. We reviewed them in depth, and here I'm going to only show new features. So for the next one, let's have plot t sine of t minus pi. And then for the markers, let's have BS. Okay. So I'm going to run this. As you see, I have 3 plots in here. Plot 1, plot 2, plot 3. So I expect to have 3 plots shown. Once I run the code, I see that only 1 plot will be shown. Let's do an experiment in here. Let's turn them into comments so they're not run. So if I run the function again, you see that the exact figure is produced. It means that the first 2 plot codes, they're not run. Or better say, they were executed and then overwritten. The process is like this. The first line is executed and will be shown. So let me actually show to you what happens. So the first time, this will run. But as the second code will be executed, the first one will be overwritten. And once the third one is executed, the previous 2 ones are overwritten, like this. But this is not something that we want. We wanted to have all of them together. So there is a function, or better say code, called hold on. And all it does is that it keeps the figure and the plot, the first plot on it, so the later ones will be shown as well. So if I run, you see that now all three of them are shown. So this will keep this plot on as long as we have the code in here. So any plot you execute after the hold on will be also stored and shown on the same plot too. So in order to turn this feature off, we use hold off. And now let's run another plot in here, and then let's have pi over 3. Okay, and then let's use G in here too. As you see, the previous plots were overwritten by the last one because we have used the hold off. Now if I make this one comment too and run the plot, you see that that one stays as well. This is really, really important. It enables us to actually run and show multiple plots on the same figure. Let's have more example of this. So let me create another script. Let's say plot example 2. Okay, in this one, I'm going to first create 2 plots, and then I'm going to show how we can use the subplots and then replace them as well with the hold on. So the first one, let's go clear all CLC, and then x equals line space. That was a function that you could use to actually divide the span of the x or horizontal axis, similar to the previous one, but there is a function for it right now. So I have pi minus pi to pi, that would be the range, and then y1 equals sine of x, and let's have y2. I'm going to have 2 functions plotted, cosine of x, and let's have plot. Now I wanted to have x and y1. This is the first plot. Hold on and plot x and y2, right? So this one would be first plot, and this one would be second plot. Okay, so if I run this, forgot to actually put it here, plot. Let's see. Oh, because we forgot to close the figure. So let's have clear all, close all. And now the plot is shown for x and y, for the plot 1 and plot 2. We can also use legend, and we get to it later. But I just wanted to show you that similar to the previous example, we plotted 2 functions in here. Alright, so in the next step, let me create some subplots and then show you what will happen if we continue with that. So let's have hold off for now and add another y. I call it sine of 2 pi, and then plot x and y3, which make it, oh, I noticed that instead of x I put 2 pi, no wonder. Okay, now I just shown the last function only and not the other ones. So let's get to subplots. Okay, so I'm going to call it example 3. Plot x3. So again, I will call clear close all names DLC. Okay, in this one, axis 1 equals subplot 2 by 1 by 1. And if you remember, what it does is that it creates 2 rows and 1 column and 1 plot, and selects the first, actually the first figure or plot. So imagine that it is rows and it is column, and we're working on the first figure in the top. And then let's have x line space 0 2 pi. And then the first plot, let's have sine of x, plot x and y1, first plot. And then axis number 2 would be subplot 2 by 1, but this time second one. And then y2 equals cosine of x, plot x and y2. Alright, so in this way we actually created second part. What is wrong with it? Unbalanced or unexpected parentheses. Where we did that. Line number 5. Oh, here we go. It's better always to check your code to make sure that everything runs correctly. So right now we have shown 2 plots on 2 subplots, and we're going to actually use the hold on and hold off that we learned right now and manipulate the functions. So in the next line I would use hold. But right now I have 2 figures or plots instead of 1. Previously it was easy because we could use hold on, hold off. We had only 1 plot, we knew how to handle it. But now we have to learn how to actually work with 2 plots. So we specify hold axis 1, and then we put this in single quotation and on. All it does is that it holds the axis 1 on, and then y3 would be sine of something we create, 2x, it's a new one. And then let's have plot axis 1, x and y3. Right? So right now we're plotting the y3 in addition to the previous ones. So let's have the plot, and it's better to suppress the output. Right now you see that the first plot has 2 figures or plots shown. The reason is that we specifically mentioned that axis 1 should be hold on, but not axis 2. Now let's hold axis 1, and then this time I make it off. The same way, once we have hold axis 1 on, now we can turn it off. Let's have y4 equals sine of 4 pi, x, and then plot axis 1, x, and of course y4. We want to see what happens when we have hold axis 1 off. So if I run this, what happens is that 2 previous plots are gone, and they're actually substituted or overwritten by the new one. The same way we can manipulate all other plots and show new or replace them with new plots. Hope you enjoyed this video, and I'll see you in a new one with more examples. Hello everyone, welcome back to another episode of MATLAB programming. In this short video, I'm going to show you another useful feature when it comes to plotting. It is called related properties. So we knew that we had multiple options to change and customize our plots and graphs and show the data in the best way that represents the solution of the program. I've created a script and with some examples in it. So there is something called line width, which, you know, self-explanatory. It creates and changes the thickness of the plot or the line. The next one is maker edge color, and it specifies the color of the marker or the edge color for the field markers. For example, if you decided to show the circles, dotted circles on the plot as the markers, you can specify what color should be the edge of those circles, and I'm going to show you in a minute. And the next one is marker face color, which is the field color of the circle or any other marker that we use for our plotting. And marker size is the size, how big that markers should show on the plot. So let me give you an example that clarifies this feature. Let's have clear all, close all. Actually, get rid of this, CLC, and then we have t as input equals 0 pi over 2. Let's make it bigger, 15, and then 2 pi. This would be the x-axis or the horizontal axis. Then let's have plot t and sine of 2t, and then I'm going to use these relational markers. The first one I use dash mo as before, and then I'm going to, because it's going to be a long one, I can actually use 3 dots. If you remember, that takes you to the next line, and then here I use the first relational function that we learned today, line width. Make sure you type the capital letters as appears here. And the line width we specified as 2. So then again, 3 dots, next line, and then we have another marker. Let's have edge color. And for this one, let's have K. Three dots, and then let's have marker face color. And then for the face color, you can use different things. Here I'm going to use the RGB color, which specifies the intensity of the conventional RGB color spectrum. 49, 63. And we're going to work with these numbers in a minute and show you what these means. Okay, and the next line would be the last part that we learned, marker size, how big it should be. Let's for now select it as 10. Okay, so we have written a plot function in here that has all these relational properties. So let's run them. As you see, this is the graph that we received. So the K here, or line width, let's start with this one. Line width is 2. Let's make it 5. You see that the thickness of the line is now different. Here the M, let's make it R. It should turn it to red. And let's make it 3. That was too thick. Okay, much better. Marker edge color. This is K, which stands for the black. So the color around it is black. Let's make it blue. So here we change that one too. And then marker face color. Face color is the field color in here. Let's change this 63 to 98. Just a number you pick, and it should be between 0 and 1. It cannot be more than 1. So now the color is different. Let's make this one half. So you see that the face color is different. Make it this one 6. So it is also different. So you feel free to, change any number that you like and see what are the consequences on that. Let's make it 1 and make this one 60. Let's run it again. So we see that it's now changed a lot. 4, and the blue changed it to green. Oh, the edge color, let's have it black. This one is okay. Probably this one here too. So you see that you can, manipulate the plot very easily. And the marker size, the last one is 10, which it shows how big they should be. Let's go with the 1 actually. You can see with the value of 1, it is barely visible. So it's better to make it bigger. Let's go with the 5 value. And once you run it, it's better. And also we can make it something much larger, which is not very practical in this example, but the point is that you have unlimited capability to change whatever feature you like, to adjust it to your own program and make sense of data. I hope you enjoyed this short video, and I will see you in next episode. Hello everyone, welcome back to another episode of MATLAB programming. In this video, I'm going to show you how we can set the limits on the plots and show the graph within a certain axis limits. So, and it is very, very important because most of the time there are functions and graphs that are shown within a certain limit and axis, and only then we can evaluate and analyze the data correctly. So without any further ado, let's get us started on that. I'm going to create a plot graph. Okay, and let's start here, CLC, and then let's get a start with x equals line space. Let's plot it between 0 and 2 pi. And then let's have y equals to cosine of x. And then plot will be x, y, and let's have red. Very simple. So let's run this. Okay, so the graph is shown in this axis limits, and we're going to see how we can manipulate that. If we run the function or the command axis, and the format is that you put the margin and limits within brackets. So I'm going to say 0 from 0 to 2 pi, and then minus 1.5 to, or better say 2, minus 2 to 2. Okay, so what does it mean? It means that show the x, because the first variable in the plot is x. So the axis limits for the x would be from 0 to 2 pi, and for the y will be minus 2 to 2. So let's graph that. And if you see that the graph now shows from minus 2 to 2, and from 0 to 6, which is roughly 2 pi. Similarly, we can use the same function for more complex problems, like in space from minus 10 to 10, and then divide that by 200 points, and then for the y equals sine of 4x, and then divided element by element over exponential of 0.1 x, and then plot x and y. Axis would be, just try the values that I put in, and then you can manipulate the values as you like using the M file that I provide you with. Then from minus 10 to 10 would be for the variable x, and then 0 to infinity for the variable y. Okay, so let's try that one. You see that now the x is shown from minus 10 to 10, and the y from 0 to infinity. Okay, I categorized the examples with the coding here, so you have all the M files related to the examples that I run here, and you can try them as well. So for the example number 3, let's have another problem. Then space 0 to 10. I'm going to use subplots here. Let's have it 100 points, and then y1 equals sine of x would be x1 actually, and then ax1 equals subplot, let's have 2, 1, 2, 1, and 1. So 2 rows and 1 column considered like this, and we're selecting the first plot. So for that one, it's going to plot sine, and the next one, x2 equals, in a space 0 to 100, and let's divide it by 5. And then y2, let's have again sine of x2. And then ax2 is going to be a new variable, subplot. Now we're selecting the second plot, which is going to be 2, 1, 1. I'm sorry, 2. It's going to be the second one. We already addressed the first one in here. So we're going to plot x2, x2, and y2. And now let's put the axis ax1, ax2. I'm going to show you a new format here. And then 0 to 10 and -1 to 1. I'm sure we can guess how this axis function works on this new format, but it's nothing new, but it's showing 2 variables instead of 1 in previous example. So let's run these. Before doing that, let me make all these comments. Alright, so now it should run, and we should see the plots in here. Oh, I forgot to actually plot the first variable. Okay, so plot, let's have x1, x1, y1. So now we have 2 subplots. Now we have 2 subplots as expected. And as you see, the axis 1 and axis 2 is shown on one bracket, and the axis 1 is corresponding to the subplot number 1 and axis 2 to the subplot number 2. So what is common in here is that the limit for 0 to 10, which you can see here, is common for both axis 1 and axis 2. Similarly, -1 and 1 range is similar for both of them. It's common for both of them. So you see that we used it in a very smart way. Instead of writing 2 lines of code and 2 axis functions, we just combined them in one and used it once. And it's very useful and removes the code complexity very much. In this video, we're going to cover a very useful and handy feature in MATLAB, and that's called link axis. That comes really useful while using plots. So let's get started with that. Let me first create a range for x1 equals 1 to 100, and then y1 would be square t of x1. x2 range would be from 1 to 100 as well, and then y2 function would be sine of x2. Okay, so we define two functions and we want to plot them. So I use the figure to bring some figures in. Subplot, I would like to have 2, 1, 1. And then I'm going to have plot x1, y1 on the first. And then subplot 2, 2, 1, 2. And on that one, I'm going to have x2 and y2 plots. Okay, so we have defined two simple functions, and then I'm going to have plot them on two different subplots, and I will explain on that what's going on. So let's run this. It will bring up an image. Let me zoom out so you could see clearly what's going on. So we have defined both functions from 0 to 100, starting from 0 to 100. Now look, if I try to zoom in the above plot. So as I click on that one, you see that the scale on the first plot changes, however not on the second one. So let me zoom out again, and I'm going to do the same with the bottom plot. So as you see, the ranges will differ while the above range will stay the same. We don't want it to have this. We want it to have both functions linked together. So once we zoom in one, the other one will zoom in as well. There is a function in MATLAB, and that function does exactly that thing. It's called link access. So if I type link access, we need to have two variables defined in here, and then we refer to those variables, because we cannot copy paste the whole subplot in there and run the whole thing. So I will define this as h1, this first subplot, and then the second subplot as h2. And then in here, I would refer to h1 and h2 variables, and I wanted to specify which axis I wanted them to link to, so they will. Now, if I run the whole thing, it will generate the same plot with a very distinctive feature. Now, if I zoom on the above, this subplot will also zoom out, and the same. It's a very handy feature and quite useful when you wanted to maintain the scales for both plots. In this video, I'm going to cover the function topics. In previous course, we briefly touched this item, and since it's a very important topic in MATLAB programming, I'm going to give you multiple examples on this, and we're going to cover a wide range of applications that comes with this useful function, and also how we can define the user, actually how we can create the user-defined functions in MATLAB programming and manipulate the data as we wish. So just to remind you, we learned previously that there are different ways to create user-defined functions. The easiest way would be to go here and select function. And I would like to add that depending on the version of the MATLAB that you're using, this menu might be different. But since 2012, if I'm not mistaken, the interface of the MATLAB were somehow consolidated so you can see very similar experience all over different versions since then. So back to our topic, for the function, if we select this, MATLAB will create the complete format for the function. It has output arguments, input arguments, and the name of the function. And if you remember, the important thing is that the name of the function should be exactly as the name of the M file. If these two are different, you will run into error. And also the end that closes the function. It's conventional to put a comment after the function that explains how this whole group of code actually works together. So let me actually delete that and show you another way too. You can create a script and then transform it into a function. So let me save it. I'm going to call it area calc. I'm going to show you how to calculate the area of figures, like radius, like square, rectangle, and all these simple examples that can give you a better idea about it. So function will start with the word function, which is reserved, and then the output argument, which will be area, equals. The name of the function that we just mentioned should be exactly as the name of the M file, area calc, and the input argument in parentheses. The input, for now, I'm going to calculate the area of a square, and then therefore we only need one argument in here, and that's the length of the side. And then of course the end, which closes the function. So for the function value, now we have to show how does it work. The code inside it, how does it work? It's like using the sine function in MATLAB with many internal codes that you cannot see, but MATLAB already knows how to calculate the sine value for any argument that you pass into it. So the area would be A multiplied by A. Let me put a comment in here too. This function will calculate the area of a square. Okay, and then A is the sine squares. Okay, now that I've defined the function, MATLAB knows how to calculate the area, actually the output argument, how to calculate the arccalc function that we just defined for MATLAB. So let me run an example. Area calc of 6. It means that we're telling MATLAB to calculate the area of a square with side length of 6. I misspelled it, so when you type it correctly, you get the result. One more time, but this time we're going to use, let's say, 2, which means that the square sides are 2. So we get the result of 4. And we can build up on that and use fprintf. And then in here, I would like to use the area of the square is, and then square, floating number, next line, and then what is the value? It's going to be area. So I will run area calc 4, and now the area of the square is this value. Let me actually modify that. Area calc of 5, and then the area of the square is 25. because the 25 is the output that we defined in here. This is the variable. Similarly, we can use the same experience for a circle. So let me put this one actually in case 1 square, and then the area would be calculated like that. And then I would like to use case 2, circle, and then in here this function will calculate the area of the circle. Okay, and then the area would be pi multiplied by radius and radius 2 times. So now in here the input argument is no longer a, it will be radius, and then the area will remain the same. Instead of here I use circle. Now if I pass area of, let's say, 2. Oh, I'm sorry, made a mistake. Area calc of 2, it will be, the result will be this, because now the input argument is radius. So this was case 2. Let me should mark that, and then let's go to case case 3, which will be rectangle. So we will use this function will calculate the area of a rectangle. Okay, in rectangle we have 2 sides to multiply together. So now it's more complicated. It's still very simple, but the idea is actually expanded into 2 dimensions. So let's write the area. Area would be A multiplied B, right? And then let me define here A and B are the rectangle sides. Okay. And then what we need here, because we have 2 input arguments, here we have to actually have 2, A and B. We need to pass 2 input arguments to this function to work. And then here the area of the rectangle is value this an area. Very simple. CLC, and then let's have area calc of 2 and 3. And the area of rectangle is 6. You see, this simple example just showed you how we can manipulate the functions and create user-defined functions, because we actually cover it in a much more detail in coming chapters. But I just wanted to show you how powerful and time-saving this function is. And no matter where in the MATLAB environment you are, and you may be doing some, plotting or running some other example like the ones that we actually did previously here, you can call the area calc of any number. Let's say the last one has 2, area calc of 2 in here, and then run it. It just runs the code, and then when it gets to this line of code, it just calculates it. So the good thing is that these functions can be recalled anywhere in any function. You need it to, do the same thing, and you can use it. You can create it once and then recall it every time. It will save you a lot of time, especially in cases where you have multiple repetitious calculations. It will save a lot of time and make your code much simpler than it should be. I hope you enjoyed this session, and I'll see you in the next video. In this video, we're going to explore one of the other features of functions, and that's how to get 2 or more outputs out of one single function. Previously, we learned that every single function has one output, and we can get the results once we type the input arguments. So let's explore that. In this example, I'm going to create a simple function to calculate the area of a rectangle. And then later, I wanted to add the circumference of the rectangle as an output variable and call both the area and circumference together. So let's get started with that. I will create a, so we can create a function in here. This is the format that will bring output arguments, identified input arguments. So output arguments, I have area equals the name of the function. I would like to call it FNC function test. And then input arguments. How many input arguments we need to calculate the area of a rectangle? A and B, 2 of them. So that's how it works. And then there's a format for A and B. The area equals, I can call it area equals A multiplied by B. And that would be it. So let me save function FNC test. Now, let me try to run the function in here. FNC underline test of, let's say, 2 and 3. A rectangle with 2 and 3 values. So the answer would be 6. However, we learned that the area is an output to this function. However, you see that the answer, there is no area variable in here or here. So let me call it. When I try to call the area, I'll get an error. And the reason is that the MATLAB, once you create a function, all those variables, including A and B and area, only belong to that function, and they're not recognizable by MATLAB outside that function. So if I, let's say A, if I type A, it's undefined, B undefined, and that's not how MATLAB works. In order to calculate the area variable, once the MATLAB calculates this area, it will erase the value for area. In order to maintain that value, I can create an area variable and then put the value of FNC test 2 and 3 inside that area. So the area value will be 6 and the area variable is created in here. Now imagine that I would like to add the circumference to this calculation too. So that was the area calculation. And then I create a new variable, and that would be 2 multiplied by A plus B. And let me call it circumference calculation. I get a warning, and that's the value assigned to this variable might be unused, and that's true because here I didn't specify any output for this. As a matter of fact, if I run this area equals f and c underline test of, let's say, 4 or 5, I get only the area back. There is no circumference in here. How can I get two outputs from one single function? Well, it's a very simple modification to the original script. So I specify a new variable, the same variable in here. I can simply copy and paste it, and then close the bracket. Now our function, I don't have that warning again, and I have both output variables in here too. So if I try to get the result in here, still I receive the area, and we have to treat it the same way as did for the first time. So I create another bucket for the variable area, and you may or may not use the comma, it's not necessary in here. And there's circumference. So now the variables are calculated inside this function, these two variables, and the value will be put on the area, and the value of this will be copied to this and maintained. Now if I run this script, the circumference variable is created here too. Make sure to note that this area and circumference are different than those we defined inside this function. As a matter of fact, I will change the name of these two variables to a and b. And when I run the function, you see that two new variables are created because these variables are only containers. We calculate the value and then transfer those values into a and b to maintain them. So it's a good idea to have this practice. Once you have more than one output in a single function, you can concatenate them using the brackets and have them together. In this session, I'm going to tap into one of the most important things in MATLAB when it comes to functions. As you remember, in previous course, we talked about the inline functions, and we learned how to work with those functions to create our own expressions and use them in MATLAB frequently. However, inline is no longer supported with newer versions of MATLAB. Therefore, they have substituted that with a newer version called anonymous functions. And let me express what anonymous function is for. In MATLAB programming, and in general other programs as well, there are cases when you break a large program into separate sections like different functions or different scripts, and then call them together. And it's actually a very good way to monitor a large program. In some situations, we need to deal with certain functions that are not that big or complex that we need to break them into scripts or separate functions. We can write them in one expression only, and that's when anonymous functions come handy. So the format of the anonymous function is that we call the name of the function and @ and then in open and close parentheses, we specify all those arguments, input arguments. If it is f of t, the t variable would be the input arguments. If it is t and y, then the t and y will be the input arguments. And then the expression of the function itself. So just to show you two examples, in example 1, I'm going to use f of t, t to power 5, e minus 2t, and cosine of 3t. I wanted to write it in the MATLAB using the anonymous function. So to do so, I type f as f of t, and then equals @ what are the input arguments? So if I look at here, I have t and also t and t. Therefore, I have only one input argument. That's why I put it here, f of t, @ t. It means that the only variable in this function is t. And then without any equal sign or any other symbol, I start typing the expression in MATLAB. And then MATLAB understands what this expression is for. We used to use inline, now this is the new format. To give you a more general example, I have here the G, X, Y, A, B, C, and what it means is that, actually, let me correct it, there's no sign here. Okay, so the G of X, Y, A, B, C, it means that all these input variables are found in this function. So look at that. X is an input variable, A is 1 minus B, X we have found it before, C and Y. So we have 5 input arguments in this G function, right? So the way that we write it in MATLAB is G equals @ X, Y, A, B, C, X to power A and blah blah without any symbol after this expression. Okay, so this is the format. Now that we have, learned how to deal with this new anonymous function, we're going to solve a couple of problems on it so we can make sure that we master it. Therefore, let's get started with MATLAB. In the first example, I'm going to use f equals @ I'm just typing the format that we discussed here. Count 5, expression minus 2 t cosine of 3t. And make sure that you put the dot for element by element multiplication before this expressions. That's very important, because if you don't, then this function will not work over the ranges. It will work only on single points. So let me, this is the function that we defined, and now I'm gonna try to evaluate it for different ranges. So this is t. Now imagine that I have a variable called x, and the x would be from 0 with increment of various small points. Actually, let's make this and 1, for instance. Okay, so that's going to be the range. Okay, make a mistake here. That's going to be 0. Okay, so that's the range, and let me put our f function in here too. Now I'm going to evaluate it. So f of x, I'm going to make a new function, would be f and x. So once you define what the f function is, then you can pass any variable to it. So we define the x variable to be this one, right? The x variable will be this one. And then I'm going to pass the x to f. That's the result. You see that how handy this function is. We just created a range, anything that we wanted, and then passed to it. Let's say f of -2. It just calculates it for you. F of sqrt of 90. It just does it very fast. So let's do another one. I'm gonna define a new range, random of 6, right? It's gonna create a 6 by 6 matrix. So I'm gonna create f of a, and that's f of a. I'm gonna pass the matrix, this a matrix, to the function that we specify, and MATLAB would calculate very, very easily. That's a really, really handy function to work with. To show you the differences, let me bring this function, and I'm going to eliminate the dots in here. Okay, so I redefined f, and now I'm going to have f of 3 would pass this. However, if I'm going to have f of, let's say, a range -1 to 1, Okay, this is a range I defined from -1 with increment of this unit to 1. So I'm going to pass this to MATLAB, and then you don't get the result because we cannot do it without putting the dot in here to do multiplication, because that's a range. And now if I do it and then f of this, it will solve the question very easily. Let me clear the screen. And you know, these expressions or these functions that we define, they're useful, and MATLAB actually utilized that already in MATLAB. For example, I'm going to redefine f, or let me call it g, equals at cosine. That's it. So cosine is a function that MATLAB has already implemented into MATLAB library, and I can call it so g of 0. So MATLAB already knows what is it. I'm going to have f equals at sine, okay, at sine, and then I'm going to have f of 0, it's going to be 0, f of pi over 2, 90 degree, that would be 1. So you get the idea how useful this function feature is in MATLAB programming. Let me give you another example, and let me bring up the PowerPoint in here. I'm going to have a new slide. Okay. One of the most frequently used MATLAB functions is the stepwise function, and that's when you have, let's say, a t. I'm going to call this t of x equals, and stepwise is that you have two different functions inside one. So I'm going to have, let's say, x. I'm using x because the x variable, I've defined it here. And that's true for any x, a member of -1 and 1, between these range actually, not range, 1 and -1. And anything else, that would be 1, okay, for anything else. So otherwise. I'm going to see how I can define this function in MATLAB. So let me first draw it here. If I'm going to use -1, the result would be, so -1, 1, and anywhere else. So -1, that would be 0. 1, also 0. Anywhere else, it's going to be 1. Okay? So anywhere else between these, it's going to be. That's the function that we're going to create in MATLAB. So let's get back to MATLAB environment. We're doing this using Heaviside. So let me duck Heaviside function. So the Heaviside returns the value 0 for x less than 0, 1 for x larger than 0, and half for x equals 1. So we can utilize that actually in MATLAB. In here, I'm going to have t equals at sign, and then x, because that's the variable we're going to use. And we're going to have Heaviside of x plus 1 minus Heaviside of x minus 1, and multiplied by star 1 minus absolute value of x. So that's going to be the function. So x plus 1 and x minus 1 in here. If I type 1, then the value would be 1 minus x. If I type minus 1, the value would be still 1 minus x. That's the Heaviside x minus s multiplied by this value. And 1 is otherwise. forgot something. That's not balanced. Okay, so I defined the t, and now if I, let's say, type t of 0, that's 1. T of -1, that's half. It's interesting. We typed something wrong in here. So let me type 1. It's 1. Okay, let's look at that. Okay. That's gonna have 1x in here. So let me look at this, what's going on here. Alright, so let me clear and then do t, and then let's have t of 1. Oops, can't type today. 1, and then t of -1, and then t of 0. Okay, now it works. It was an unbalanced expression. I'm going to leave it without editing this video, so you can see that, you know, sometimes it happens. You have to kind of like dig into it and find the reason that is causing it. This was one of the most important features in function definition in MATLAB. And before we close this section, I'm going to introduce you to another feature in MATLAB, and that's called once you wanted to actually plot a function as an argument. For example, just doc is plot. If you do that, the isPlot, it has a lot of features that you can use and utilize. So isFile plots the expression f of x over the default domain, right? And then you can actually specify the domains for it as well. So if you come here to examples, it will define, you know, consider just the normal domain over -2 pi over 2 pi, and so on and so forth. Searching for a type. Okay, so let's see. isPlot of at sine, because sine is already defined as type of function already known, and it calculated over -2 pi over 2 pi. So we see that, and I can do isPlot of tangent. Okay, so that's tangent, and you know, you can use multiple functions in here. Let me use let me introduce you to fplot too. Fplot is doc fplot, and all it does is that it gets the limits, so you can specify the limits that you want the MATLAB to kind of like plot the function over to. But it comes really handy once you define the function already. For example, if I have, let's see what I have here. Command. Okay, so I'm going to type it here, f of t, and then I'm going to have fplot at t at f, that's the name of the function, and then I'm going to have it over a range of -1 to 4. Okay, that's the function I'm going to have. Let's see, okay, it's used already as a variable. Okay. I see, because I've used it as a variable already. So let me have something easier. is plot of that sign, and then over a limit -1 and 4. So it's gonna just plot it over the range that we want to. And you can specify the ranges and use the functions that are already known by MATLAB.